Hello everyone, this is Dr. Feng Wang again, and today we are going to discuss carboxylic acid, chapter 19. So this is a very short chapter, and many of the concepts actually have been covered either in GenChem or OChem 1. So this is the structure of carboxylic acid. It's the whole thing here: carbon, oxygen, carbonyl group plus OH group. So in this type of configuration, again the whole thing is considered a functional group. It's called a carboxylic acid. We cannot say, oh, this is ketone, this is a hydroxy group. No. This is the property of this group is quite different from hydroxy group, and this group is not a ketone group because again the hydroxy group is on the right side, although the left side is a methyl group. So the typical structure of carboxylic acid is first is acid. The 3D structure of the acid is, this is the central atom of the acid. And this is carbon, is sp2, hybridized carbon. So the shape around this carbon is a planar structure. You see, it is a planar structure, trigonal planar actually. The bond angle is about 120 degrees. So as usual, the structure, the naming, IUPAC naming system, the physical properties, and the spectroscopic properties of a carboxylic acid. I think that they are, just some numbers here. I think they are easy. I ask you to read chapter 19 from first part to the fourth part. So if you have any question, please either call me or send me an email in this part. We actually learned many reactions that can be used to prepare carboxylic acid. Here in this chapter, I will not provide you the details, but if you want to know the mechanism of each reaction, I would suggest you to review the details in the previous chapters that we have discussed before. The first reaction to prepare carboxylic acid is the oxidation reaction. If we oxidize primary alcohol with a strong chromate oxidative agent in acid condition, we can prepare a carboxylic acid. The second reaction is another oxidation reaction to prepare aromatic carboxylic acid. This is a benzoic acid. In this case, we need a benzene ring, we need an alkyl ring. So there is a requirement for this type of oxidation reaction. The requirement is that there is at least one hydrogen on the first carbon here. If we do not have a hydrogen here, there is no carbon-hydrogen bond, there is no oxidation reaction. Like in this case, we have 3 hydrogens here attached to this carbon, and in this case we have 2 hydrogens. We have 1 hydrogen in this case. The oxidative product actually the same. It's a benzoic acid. So regardless of the variations of the structure, alkyl structure attached to this benzene, if you have at least 1 hydrogen here, the final product, the oxidative product, is the same. It's a benzoic acid. The third reaction we learned is also oxidative reactions, because again, for acid group we have a carbon 1, 2, carbon 1, 2, carbon oxygen bond 1 2 and a 1, so totally we have 3 carbon oxygen bonds here in the structure of a carboxylic acid. So many reactions actually are oxidative reactions because we need to introduce a lot of carbon oxygen bond. So alkyne, so it is a molecule with a carbon-carbon triple bond. If we oxidize the alkynes, actually this reaction we also call this ozonolysis. Ozonolysis means we use ozone as an oxidative reagent, and the ozone breaks down the alkyne molecule, the carbon-carbon triple bond, to form 2 acid molecules. So the left side forms acid molecules. The right side forms the second acid molecules. So there is a special case. This is actually the special case. In this case, we only generate 1 carboxylic acid molecules plus carbon dioxide. The special case is for the terminal alkynes, which means the carbon-carbon triple bond is one of the carbon is the terminal carbon of this molecules. In this case, the left side, which has more or equal to 2 carbons, in this case, we are still forming a regular carboxylic acid group. But on the right side, there is only 1 carbon left. Alkyne molecules, one carbon on the right side. That's why we call this terminal alkyne, because there is no more carbons on the right side. In this case, the right side will form carbon dioxide. Well, we reviewed the reactions to prepare carboxylic acid. The next step we are going to do here is to review the reactions we learned before. So carboxylic acid, it is acid. So the well-known reaction from acid is acid-base reaction. There's a acid base. These are the concept we learned from a long time ago. Acid, why it is acid, like this is carboxylic acid. Acid, the definition here is basically the molecules can provide a protein. This is why we call this is acid molecules. And the base basically is the molecules who provide 2 electrons. The 2, like this, in this case, the base provided 2 electrons. These molecules provide a protein. It's the hydrogen without any electrons. So these 2 electrons forms the covalence bond between the base and the hydrogen. See, this is the acid-base reaction product. So the leftover is obviously is oxygen anion, because these molecules donate a protein, a hydrogen with a positive charge, to form this molecule. More examples of acid-base reactions. This is acetic acid. Very simple carboxylic molecules react with the sodium hydroxide. It's a very strong base. Well, this is well known acid-base reaction. Again, acid provide protein, hydrogen without any electron. The base provide 2 electrons. In this case, we have 3 pairs of lone pair electrons. One of them will form a bond between the hydroxyl group and this protein. So basically, this is the new molecules is water. So the leftover is the oxygen anion. So sodium cation here is just a balanced cation. So in the sodium hydroxide, just to balance the negative charge of a hydroxide. Here, just a positive charge to balance the oxygen anion here. So we compare the pKa values. pKa value of this acid is about 5. Water's pKa value about 16. Again, pKa value is a very important concept for many chemistries, organic chemistry, gen chem, physical chem. So we definitely need to understand what pKa is. So pKa is only for acid. There is no pKa values for base. So the lower the pKa value, the stronger the acid is. Like in this case, the acetic acid is much stronger acid than water. So we have the reaction favors the formation of water. The same thing here. The benzoic acid react with the sodium bicarbonate. This serves as a base. So one of the 3 lone pair electrons from this oxygen, one of the 3 oxygen here, donate its lone pair of electrons. And this molecule, the benzoic acid molecules, donate a proton. So we forms this weaker acid. The pKa value is 6.4. Benzoic acid is 4.2. The difference, you see the difference, 44.2 to 6.4, is not as big as this one. But this we can confirm the reaction favors the formation of a weaker acid, because this benzoic acid is a stronger acid. We always, for acid-base reactions, we always have reactions which favors the weaker acid. So from stronger acid to weaker acid, stronger acid to weaker acid. This one heavily favored to this side. This one not as heavily as this one, but we know the direction also towards this way, favors the formation of weaker acid. Well, again, pKa value is very critical. I don't want you to remember exact numbers of the pKa values of the acid in this table, but at least you should have an idea the rough range of molecules pKa. Some very common molecules like water. It's about a 16, which is very close to alcohol. And this is methanol. It's alcohol. All alcohol and water, they have pKa value about 16. This is another alcohol. Hydrogen, pKa value is 35. It's very big. 35. So hydrogen is in theory it could be an acid because it can provide a proton in theory, but because it's a high pKa value 35, so hydrogen is a very weak acid. It's rarely to see hydrogen gas molecule serves as an acid. Well, this side actually is the base. If we call this as acid, then we call this side is conjugated base. Or we can use another set of terms to define the molecules on the left side and the right side. So another set of terms is we call this base. Then this is conjugated acid. Basically, it's you gain a proton or you lose a proton. You have a proton here, you have the hydrogen, it's acid or conjugate acid. If you lose the proton, then you are considered a base or conjugated base. So the trend, the normal trend is that lower the pKa value, the stronger the acid. The lower the pKa value here acid, the stronger acid, but its conjugated base is a weaker base. So if you have a very high pKa value like hydrogen, very high pKa value, so it is a very weak acid. But its conjugated base, this is a hydride, hydrogen with 2 electrons. It's called a hydride. Hydride is a very, very strong base. Ethoxide or sodium hydroxide, they have a lower, they have a lower pKa value. So from here and above, they are weak acid, but their conjugate bases are considered very strong bases, again, from water or from alcohol. pKa value around 16. So if a molecule's pKa value is equal or above 15 or 16, then they are considered a very weak acid, but their conjugate bases are considered strong bases. Alright, how we know the acidity, how we compare molecules with different structure, they may have a different acidity. So we learned in OChem 1 how to compare acidity of different acid molecules. Let's take a look. The first acid molecule, again, is very simple. Acetic acid, pKa value about 5. So acid, again, is basically the provider of a protein. So this molecules provide a protein. Protein is considered acid. Okay, the leftover is an anion, oxygen anion here. So it really depends on the stability of this anion. If we have a better stability of this anion, which means that this molecule, well, I'm going to form a stable, relatively stable anion. So I'm willing to generate a protein, which means it is a strong acid. If the conjugate base stability is very bad, I can provide a protein, but I'm going to form a very bad, molecule with a very bad stability. The conjugate base has a very bad stability. You know why I want to do that? I don't want to generate a protein because the stability is too bad. So in that case, the acid is considered a weaker acid. So in the case of the acetic acid, we generate an oxygen anion after we generate a protein, the acid. So we can draw our second resonance structure. So the 2 electrons move this way, 2 electrons move this way. So to form a new resonance structure, so we used a double-headed arrow to represent the 2 resonance structures. Again, resonance structure, basically, you have the same configuration, which means all atoms under the same position. You have the same sigma bond. Each atom has the same between 2 atoms. The sigma bond are they equal. 1 sigma bond, 2 sigma bond, 3 sigma bond. They are identical. So they are considered a resonance structure. So when you draw resonance structures, you basically move either lone pair of electrons or pair electrons to form a new valid Lewis structure. So by a resonance structure, we see the negative charge, the unstable point, location of a molecule is the charge. Nobody wants to bear a negative charge. So when we do the resonance structure, we basically shift the negative charge from this oxygen to this oxygen. So this is a hybrid structure. So there is a full negative charge in this molecule. The final result basically each oxygen atom share a half negative charge. So in this case, we see acetic acid is not a very strong acid, but a decent acid, because again, the conjugate base, the stability is not very bad. So negative charge causes the instability, but the negative charge can be distributed between the two oxygen atoms. So it is a decent acid. Well, let's take a look at other two molecules. One is alcohol, another one is phenol. Both molecules have hydroxyl group, OH group. So if we check the pKa value, alcohol's pKa value above 16. The phenol is new to us, so we didn't learn phenol in Chem 1. So phenol's pKa is 10. So both molecules are weak acid pKa values, pretty big. And we know from the pKa values the phenol is much stronger acid than ethanol. This is ethanol. So which means the phenol is easier for phenol to provide a protein here, much easier than the alcohol ethanol. Although the phenol is hard for phenol to provide a protein that's the acetic acid. Let's take a look at why. So again, when we compare the acidity, we basically compare the stability of its conjugated base. Ethanol conjugated base. This is phenol. If we consider phenol acid, this is a conjugate base. We just compare the relative stability of ethoxide, oxygen anion. This is oxalate. This is also oxygen anion. In this case, this oxygen has to bear the negative charge by itself. There is no resonance structure at all. However, in the case of phenol, we can draw 1, 2, 3, 4 resonance structures. Basically I consider them, the benzene ring is a very good neighbor because oxygen bear a negative charge. That causes the instability. However, this instability can be shared with the different carbons, this one, this one, this one, and back to this structure. So which means this conjugate base is more stable than this ethoxide. Or in other words, okay, I provide a protein, I forms a less stable ethoxide. So I'm unwillingly generate this ethoxide. Or in other words, I'm not very happy to serve as a protein because this is not stable. However, in the case of phenol, it's not stable to generate oxalate, oxygen with the negative charge, but I have a very good friend. They share the negative charge with me. Or in other words, we say this phenol is more willingly to generate a protein than ethanol. That's why phenol's pKa value is lower than ethoxide, or the acidity of phenol is higher than ethanol. All right, again, we list all three acids. We just compared in this figure. So we compare the acidity of three molecules here. So first thing we need to do is draw their conjugate base structure. Then we compare which one is more stable than the rest. So the more stable one is the stronger acid one. The inductive effect in carboxylic acid, this concept already covered in Chem 1. We use the same technology to compare the acidity. They are same, they are all carboxylic acid. So we draw the base. So again, the instability is caused by the negative charge. if we have a very strong the electron withdrawing group, which stabilize this anion. If we have an electron donating groups, which makes the instability even worse. In this case, this is a weaker acid because I'm not willing to give the proton to the base compared to these two brothers. Alright, this is a different inductive effect. Again, the electron withdrawing group increases the acidity. This is about the carboxylic acid strength from the aromatic acid, carboxylic acid, benzoic acid, and its derivatives. You know, this is without any substituent. This is carboxylic acid. So if we have an electron donating group, so the pKa value of benzoic acid without any substituent, the pKa value is 4.2. If we have a donating group, so actually decrease the acidity because the instability of the conjugate base is from the anion here. So I'm not stable because of the negative charge. If we have an electron donating group here, you see, okay, I increase more the electron's density on this oxygen atom or this oxygen atom. That's caused more instability of this conjugate base, which means that the acid is a weaker acid than the benzoic acid. However, we have other substituents which are electron withdrawing group. These groups withdraw the electrons from the benzene, from the groups, the acid group attached to the benzene. Alright, so this is a conjugate base of this acid. Again, the instability is from this oxygen anion. At this moment, you see, I have an electron withdrawing group. You are not stable oxygen. You are not stable oxygen because you guys share the negative charge here. However, this electron withdrawing group, I will pull the electron away from you guys to stabilize the conjugate base structure. In this case, the acid, back to the original acid, I have a very good neighbor here. I'm more willingly than this guy to generate a protein that's acid. Oh, in other words, we see this molecule with a strong electron withdrawing group is a stronger acid because it's more willingly to give its protein to base. This table we already learned in chapter 16. Basically, the electron withdrawing group, electron donating groups. Again, I cannot ask you because it's not that easy to remember each atom, each group, and their order. But there are some trends here. You see, if there is a carbon-oxygen double bond, carbonyl group, normally they are strong electron withdrawing group. So atoms with nitrogen, oxygen, they are normally the alkyl group, they are electron donating group. But here, this is a nitrogen. Why this nitrogen is very, very strong electron withdrawing group? Because you see the difference between this one and this one. This is nitrogen has a lone pair of electrons. So it can give other. But here, this nitrogen has a positive charge. There is no lone pair of electrons at all. Instead, this nitrogen has a pure positive charge. I have a positive charge. I always want to give my positive charge to the others. Or in other words, I always want to pull electrons towards myself because I'm positively charged. I want to get electron to neutralize my positive charge. That's why this nitrogen is a very, very strong electron withdrawing group. But this nitrogen is a very strong electron donating group. Well, again, I'm not a big fan to remember everything, although would be very easy for me to see. I would like you to analyze, to fully understand the structure, which is more important than memorize too many things. All right, that's all for this chapter. This is the homework. And again, if you have any question, please contact me.